Lastly is optical activity. So when it comes to molecules, they display optical activity, meaning how they interact with plane polarized light. So there's an important thing. We're not going to do the calculation part of this. The enantiomeric access all of that. But the optical activity is an important property to mention. The chemical and physical properties of enantiomers are identical. So they can have the same melting point, the same boiling point, etc. But they don't have the same optical activity. They have different optical activity. So they would have the opposite optical activity. So two enantiomers have identical physical properties, like we said, except how they interact with plane polarized light. So there's one thing. We have something called a polarimeter, or polarimeter. Polarimeter is simply an instrument where it has a light source, and if you know light spins in all kinds of directions, it oscillates in all kinds of directions and planes, but you have a polarizer, and the polarizer is basically found if you have polarized sunglasses. That's what it does. It simply makes the light go in one plane, and that's why it's called a plane polarized light. So the light waves oscillate in a single plane. So they're just going now in a plane. All other ones are filtered out. The interesting thing is if we have achiral compounds and you put that in here, and light is interacting, the plane polarized light is interacting with the achiral compound, it is not going to change the plane of the polarized light. So you put an achiral compound here, nothing is going to happen. The light is going to come out plane polarized. So we say it's optically inactive. Keep that in mind. Optically inactive means it does not interact with the plane polarized light. With chiral compound, we see something very interesting. When you put them in here, the chiral compound rotates the plane polarized light at an angle alpha right here. It's measured in degrees. It's called the observed rotation. So if it does rotate plane polarized light, we say this is an optically active compound. So chiral compounds are optically active. And what is this rotation? The rotation, if the rotation is clockwise, to the right from the noon position, from the 12 o'clock. So like that. That would be dextrorotatory. And you're given it label D or plus. Plus is used more often. So plus means, again, to the right. If the rotation is counterclockwise, then that would be negative, and it's called levorotatory, or a negative L. Just remember, L is for left, and that's a negative. What does that mean? So suppose we have, and I'm going to just wrap up with this. Suppose we have this compound. And we would like to check its optical activity. So what is the enantiomer of this? We should be able to draw that. It's right here. Now, let's say, okay, if we do this, this is 1, this is 2, this is 3, and obviously the H is 4. So that's what R. And of course, this is, since this is the enantiomer, this is going to be S. So there's the one thing that you need to realize is that if this one rotates plane polarized light at an angle of, let's say you get negative 18.5 degrees, this one will be positive 18.5 degrees. Now so the enantiomers, okay, rotate plane polarized light with the same magnitude, meaning the same extent, but different, or same angle, different rotation. Or you can say, you know, the direction, positive or negative. Now, I did this on purpose. You might say, hey, wait, R to the right, you know, that's a positive. There's no relationship between positive, negative, dextrorotatory, and levorotatory with R and S. So R doesn't have to be a positive, or S doesn't have to be a negative. You can have S with a positive or a plus rotatory, or you can have R with a negative. That's absolutely fine. So if we were to name this is how the name would look like. So obviously this is an R. And of course we have two groups. We have two carbons. We have 1 and 2. So that's an ethyl. So that would be R1 bromo 1 chloroethane. Of course, we have to put both of them. So since we have, so we say 1R and 1R. Because it applies to the chloro and the bromo, just remember that. So if it's a negative, all we have to do is just put a negative in parentheses at the front, like that. Negative R, 1R, bromo, chloroethane. 1 bromo, 1 chloroethane. Same thing here would be positive 1R, sometimes just written as RR, by the way. 1, or sorry, this is SS. Butane. And the last thing I want to end with is if you have enantiomers, if you have the R and the S in a mixture, there's a name for this, and you should know the name for this because it's used a lot in the medical field. This is called a racemic mixture. A racemic mixture is if you have R and S in the mixture. And a racemic mixture is achiral, meaning it does not rotate plane polarized light. So therefore, the angle is going to be 0. There's no spin. So keep that in mind. If I put R and S, then it will be 0. Because guess what? They cancel out. The rotation is going to cancel out. That makes it achiral. In optical activity. Very well. I know it's a big lecture, but it's a very important one. Look at the examples in the homework. start working on them. We will do a lot when we meet on Thursday, but we have to work quickly.